Our final speaker today is Dave Kelf from Breker Verification Systems, where he's CEO. And the title of this talk is AI-based test content synthesis, an example of AI complexity management. As I said, Dave is the CEO at Breker and a well-known EDA industry participant, having run Cadence's verification marketing, driven Synopsys verification strategy, and run marketing for co-design system Verilog, Novas, Verdi, and was a CEO at Sigmatix, a wireless startup, and others. He has a solid engineering background, has performed many ASIC designs, and holds a microelectronics MSc from Brunel University, which is in the UK, for those who don't know. Okay.
Right.
Over to you. Thanks, Dave.
Thank you, Mike. Okay. So for this last presentation, what we'd like to do is actually dig in a little bit more to the technology that Breker is using on the AI side. The area where Breker is at is, as mentioned, I think by Yassine earlier, is test content development and generating highly efficient test content. We all know in the industry today, test content is a major problem, and be it UVM, SSE integration, or full validation test content, all of these areas have issues. And the Breker kind of mission is to see, how can we raise the abstraction of this test content, and how can we reuse that same knowledge? And we use AI fairly extensively in our technology for this. The big approach that Breker has taken on is essentially to try and leverage synthesis. So, we all know what RTL synthesis looks like from years ago. The technology that Breker is applying is essentially using the same idea for test content, which sounds like a really great story, but how on earth do we actually do that? And it is, of course, a fairly complex thing. I mean, it's not just random solving now. We're actually trying to raise the abstraction up to like a specification level that can be easily understood, and then generating test content for all the different platforms it needs to run on. And so, as you can see on the right-hand side here, one of the major pieces of technology we use is this notion of planning algorithms, which is an AI subset, essentially. So if we look at the tools themselves, we can see that we have a model which comes from various sources, runs through something we call test suite synthesis, which actually brings the abstraction down to a more generic kind of regular test bench. And then we run through this another piece of technology called the synthesizable verification OS that places it onto the different platforms. And both of these technologies make use of planning algorithms. So, and what I'm going to do here is actually dig into what these planning algorithms actually are, where they're used elsewhere, and how we can make use of them to pretty dramatically accelerate the production of test content from this high-level model right down to these different platforms. So planning algorithms. So I've plagiarized significantly from IBM here. Planning algorithms have been around for a while, 30 or 40 years actually, and have been heavily leveraged by IBM. In fact, the IBM Watson team makes a lot of use of them in their AI technology. Essentially, this is a system which sets up an algorithm to start with the outcome, the end in mind, essentially. So start from the outcome of what you're looking for, and then work backwards through a series of steps. And at each step, compare what's happened in the past, what needs to happen in the future, to sort of build up a complete plan to get to that outcome. So I think that's a very approximate and very high level sort of explanation of what's going on here. But essentially what IBM has done is use graph-based type design to essentially optimize out the path through a graph as they walk like through a graph, and to try and sort of figure out how we can actually generate these different tests. So that's a lot of gobbledygook. Let's actually dig into this a bit more. So this is an IBM slide that actually comes from a case study. IBM is a significant customer of Breker's, and we worked together on this quite a bit. This is a slide from a case study that they've produced. And where they were at was they were looking at using regular UVM and indeed formal verification, and had this problem that these regular techniques tend to work very well on designs which have a large number of states but over a short amount of time. So they're very good at essentially applying like a shotgun approach to a design where you've got a lot of states and you're just basically trying to target all these different states in the best way you can using random generation. And we're all pretty familiar with that, I think. What they were trying to do was a different kind of situation where they had a lot of sequential depth. So they had to get through the design and a large number of different sequences before they then wanted to apply the random generation and go after different states. And this is actually very difficult with these current techniques. And it was this that they were looking at trying to solve. So there's a lot of theory around these planning algorithms, but there's one particularly good paper. Since in the 15-minute presentation, we can't really get into all the details of how this works, but this paper actually describes it extremely well, and these slides will be up on the TestSolve website after this, so feel free to go have a look, and it really gets into mathematics of this. But essentially, the example from this paper shows a gripper, as they call it, which is trying to build up these blocks on the left-hand side of the screen here, starting with some set of blocks and achieving some goal. And you can build a graph of all the different ways that you can actually manipulate this gripper to get this goal to be achieved. And that's this thing in the middle. If you take this graph and then you flatten it out and look at all the different paths through it, you get something like what you see on the right-hand side. So now we have this flattened graph, and what we can do with a planning algorithm is figure out the best path or paths through this graph to achieve the outcome. Because obviously, if you've got, this is a very simple problem, you can already see how complex it is. If you imagine something as complex as Frank pointed out in the last presentation at IC, the number of paths becomes, an order of 10 to some huge number. And we need a better way to generate test content to find the most efficient way through this graph. And this is where planning algorithms come in. What the planning algorithm will do is start with the end in mind, and you can see these kind of black lines over this thing here. And it will attempt to work its way back through this graph to the beginning, finding the best paths through it, and using comparisons and other mechanisms to do that. So this sounds like an interesting idea for, gripper examples, but how can it be applied to actual test content? Well, you look at this and you can sort of see, well, actually, there's a lot of similarities between this and test content. So we worked pretty carefully with IBM on this subject and came out with this following mechanism. Essentially, if we can describe using a graph, starting with the verification intent and then generating stimuli from it, we can achieve this thing that they wanted to do, which is figure out a method to get through this deep sequential space in a design and open up using random generation and other mechanisms to sort of search out and test specific parts of this sequential depth. And this is very exciting because it allows us to generate some pretty high coverage test content with a lot of sequential depth, not just for block level, but actually for SOC functionality as well. And this is really the heart of this whole idea of test suite synthesis. So let's look a bit more at this. So what we basically do, I'm just going to quickly whip through this, is essentially start with like an SOC like this. If you went to a verification engine and say, hey, show me on a whiteboard how you actually want to test this thing, you'll probably get something like this diagram. We can create this in the machine, so it's a very understandable, recognizable test suite test diagram. It's hierarchical, of course, so it gets pretty involved. And then if we run the algorithm on this, the initial algorithm, all we're doing here is flattening out this graph into something that looks like this, which is all the different possible paths through this graph to generate different test content. And then what we do is we actually synthesize the test content, and that's the clever bit here. We can do things like apply coverage up front to this, so we can actually direct the system and the planning algorithm to generate the highest coverage set of test content for this. And this is what's most interesting about this. So we take a higher look at this particular flattened graph, if you like. We can see there's a lot of different potential paths, even for actually what is a pretty simple test in this case. And so what we do with the planning algorithms, we start from the end in mind, as we said before, and whip through all the different potential paths and figure out the 4 or 5 paths that are actually going to make the highest impact to this test content. And again, I'd love to get into the mathematics behind it, but it's in that paper that I mentioned, and it's pretty clever how they can form all the right comparisons, node by node, and figure out the right way through this graph. So once we do this, then we can actually come back and we can generate the test content with this, with this planning algorithm technique. But we need to go further. So this content has to be placed onto these different platforms. And for some of these platforms, a lot of the tests have to happen in parallel. They have to be concurrent. So we use planning algorithms there as well. Essentially, if we look at that same test example, we could generate serial tests for this. But if we're running this on an SoC, what we need to do is generate tests in parallel, like this. And we need to use resources like memory as well. Now, what's interesting about this is that resources such as the SD card controller in this particular design can only be used once because there is only one SD card controller. So if we're trying to set up tests to actually exercise this thing, there can never be two SD card controllers on the same line here. Same is true of the memory and the different memory spaces and all the other different components. So we could use just a regular kind of algorithm to make sure that we don't actually double up on the number of SD card controllers on this multiple, multi-thread kind of test sequence we've generated here. But what we need to do is actually figure out the most effective way of testing the design underneath this, finding bottlenecks and trying to figure out where the actual bugs are. And where we can use planning algorithms is to actually leverage all these different paths through these different multiple tests, all running concurrently, and actually come up with the most effective test to find all the sort of the most complex kind of corner case type bugs. And we can do this by starting with a spec on the left-hand side, generating that flattened curve, and then running the planning algorithms through this. So it produces a very, very high coverage set of test content, but it can do it very quickly as well. So to give you a sense of a typical case study with this, this came from Broadcom. It's a large cell phone device they're working on. They had already produced a set of tests and got an 89% kind of coverage number, 11% off the sort of the classic 100%, right? And it took them 2.5 months, and manually they created about 500 tests. This was a combination of UVM and C tests. We applied this same technique using these planning algorithms, created the model for this design. It took about 2 weeks to do this, and the ultimate sort of number of tests was approximately 10,000, and we achieved like a 97% coverage number. So this is actually, a pretty dramatic difference, as you can see, both in terms of time saving and in the amount of tests that we're actually able to generate, and the fact that those tests were extremely high quality. So this is a pretty typical example. This case study is actually on the Breker website. You can see the much more detail about what was done and how this was derived. So hopefully this gives you a sense of for test content production, how planning algorithms and AI in this case, not so much machine learning, can be used. In 15 minutes, it's hard to get into details, like I said, but this presentation will be up on the TestSolve website. And on the Breker side, of course, we have much more detail about both the IBM case study I showed and the Broadcom one as well. Any questions on that? Mike?
Thank you. Thanks very much, Dave. That was very interesting, very spot on the topic. So again, it seems that this is all being built into the tools. So does it effectively sort of come free for the customer, does it?
Well, the tool isn't free.
No, but the improvements are, yeah?
Yes, absolutely. So this is the fundamental technology behind the tool. It's actually the first time that we've gone to this level in kind of opening up the technology that we're using to provide test suite synthesis. And yes, it's absolutely part of the tool, and it's all plugged into the technology we provide to our customers.
So based on your last slide, you seem to be saving people time, actual their effort,
yes,
the simulation time, and also getting higher coverage. Yeah?
That's right. So the time the time I'm referring to here is actually the time it took to actually design the tests themselves, right? So it was a complicated test suite that the engineer was producing here, and so that 5x change was the time it took to actually go from creating a combined UVM-C test, which was happening at the signal level, of course, and doing this at a higher level of abstraction by creating one of these graph-based models, which was, and I should mention, the language that was used is a combination of C++, and this new portable stimulus standard from Accelera. So, but it's much higher level. It gives you a view of the specification at the at this graph-based sort of spec level, so you can easily understand what's going on, and it's fairly quick and easy to build this model. So that's the time saving that's mentioned here, and then of course the coverage speaks for itself, right? Once you're generating these tests, this is the kind of coverage you can.
Okay, and given the increased number of tests, did simulation time go up?
Yes, it did. This was actually partially being run on an emulator. Yes, so the time definitely went up, but it was well within the constraints that that I know the Broadcom folks were looking for. So they, their big concern was the amount of time it was taking to write the tests and the coverage they were achieving. They had a lot of emulation and simulation capacity to run this, and it was about what they kind of expected to do to perform these kinds of tests. But yes, it did.
Yeah, no, I think that's fair enough, because most people would be more interested in that test authoring time and the amount of coverage that they achieved.
Right.
Not necessarily simulation time. And with all the AI going into the cadence simulators, they would have got that time back anyway.
It has to be said that these guys were indeed running on Xilium, and they were getting some improvements, I believe, from the machine learning regression environment that Cadence was providing. Not to mention the Palladium stuff as well.
Okay, and so one last question. So how long have you been working on this, and how far do you see this type of technology?
That's a great question. So Breker started working on this with IBM in 2012, and I would say it was around 2015, 2016 when we really started working with other customers like Broadcom, and started to see these kinds of results. So it actually took quite a while to get this right. These planning algorithms, it's a pretty complex subject. But I would say now it's been in production since about 2016, 2017. And I think with the portable stimulus standard coming out and the way we're leveraging System C as well to generate this, which is relatively new, now we're sort of seeing this entering the sort of the mainstream market, whereas before it was folks like IBM, Broadcom, and one or two others who were really interested in this because they were sort of leading the charge in this area.
Brilliant. Okay, thank you very much, Dave. Thank you.
Thank you, Mike.